Hi, this is Mr. Swanson here, and today we're going to dive deeper into quantum chemistry and look at the relationships between electrons and light. Electrons and light both behave like waves and particles. It's known as the wave-particle duality. Now, that statement shouldn't sit well with you. It's weird, it's different. It's quantum chemistry. And throughout the rest of these notes, we will try to dive into a little bit of the evidence that points to this finding. But even after that, we understand if that doesn't sit well with you. And we are skipping talking about some of the famous experiments and the thought experiments and the famous scientists that have contributed to this conversation. And there's a lot more, and it's still going on. So this is just an appetizer into quantum chemistry. But this video by Dr. Quantum can really help enlighten this wave-particle duality. And he will do that through exploring the famous double-slit experiment. So go to Schoology right now and click on the Dr. Quantum video link, and then come back after you finish watching that video. Hopefully that video helped enlighten you about what we mean when we say electrons behave like waves and particles. If you're still a little bit confused, join the rest of us, and we will continue through these notes, and hopefully by the end of it, you'll have seen some more evidence to help solidify this idea. One of the main players behind this wave-particle duality was a French scientist by the name of Louis de Broglie. He discovered, or he postulated, that electrons are going to behave like waves with specific frequencies, and that these frequencies are going to correspond to the energy levels as described by Niels Bohr. And so we will take a look at the Bohr model to help better show what this means. The evidence for de Broglie's idea was this line emission spectra that you will see, or you did see, in the lab that you either did online or in school, where a sample, an element, is energized either with flame or with some current, and when that happens, it emits some kind of light. And when we filter that light through a filter, such as a prism or a gradient, it breaks it into its characteristic frequencies or wavelengths. And so you can see this pattern of like hydrogen, for instance, is broken down into 4 specific wavelengths. And that's what de Broglie was talking about. Now, one thing to look for is, this says line emission. This is the opposite of line absorption. So if you ever see something talking about line absorption, it's the exact same idea, but the picture down here is going to be a little bit different. It would be the opposite of that. So there would be colors in all of the areas that are black, and then black in all the areas that are color. We will definitely admit that the Bohr's model is not the most correct model of the atom, and it's not the most updated model of the atom, but it is a model, and we can use this model to better talk and communicate our ideas. So we're going to focus on the Bohr model because it is the most clear when we're discussing this idea, and this idea could be taken further when we talk about this newer quantum model. So the Bohr model consists of the nucleus in the center. Usually we leave out exactly how many protons, but the positives in the middle. And the real focus are the rings around the nucleus. And these electrons can exist in these rings, and they describe them as like rungs on a ladder, where the electrons can be at each of the steps, but they can't be anywhere in between. So, and we label these steps n equals 1, 2, 3, 4. So n equals 1 is closest to the nucleus. And so there's rules about how many electrons can be in these different steps. Like the first one is 2, the second one is 8, and so on. And we don't have to get into that right now, but just understand that this model, it's kind of the planetary model, is the Bohr model. And closer to the nucleus is lower in energy, and farther away is higher in energy. Now you're going to see this model many different times, and we're going to go through examples of this. And so the goal is that after you go through these notes, you could draw this and you could explain this with words and pictures to somebody else. So as we're going through it, think about how would you describe it to somebody else, like another student in your class. So let's start at the beginning. Electrons are found at the ground state, which means their lowest energy level. That's analogous to me saying, on a Saturday, where would you like to be? Well, you're going to start in your bed, and that's where you're going to stay for the majority of time until you physically have to do something. And eventually you'll come back to that bed. And so I think that's a good analogy for this. So you're starting at the ground state, and so you're going to start, for instance, right there, okay, at the lower energy levels. And if you get excited, so if enough energy is absorbed, then that electron can jump to that higher energy level. Now again, just like you getting out of bed, this is not permanent. You'll eventually come back down. That electron will eventually fall back to its ground state and then emit light. And so different amounts of energy being absorbed can dictate, does it jump from n equals 1 to 2, or does it jump from n equals 1 to 4? And so the more energy, it's going to be a bigger jump. So this diagram shows us what I would call the first two steps. So you have this ground state electron, and the first thing is some photon or some amount of energy is absorbed by the electron, and then that electron jumps up to its higher state. So that's in a 4-step process. I would say this is kind of like the first 2 steps. The second 2 steps are just the opposite. So it will eventually fall down, and in that process emitting light. So it kind of follows the conservation of energy. The energy is absorbed, and then the electron jumps up, and then it's emitted. And so it's emitted in the form of light, and how the bigger the jump down, that's the more energy. And so that's corresponds to a higher frequency of light, or a lower wavelength. So this would be a great diagram if you wanted to practice. Can you explain all 4 of these steps? This diagram has everything in the steps. And also we can talk about, like, the bigger the jump, the more energy. And so you could change up the color that was being emitted. So you see if you can figure out the 4 steps in here. Absorbing, jumping up, jumping down, and emitting. Now this diagram shows like what would happen with the different frequencies or wavelengths of light when it goes to different jumps. So again, we're starting at n equals 2. We assume the electron jumped up to a higher level. So if it jumped up to 3, it would eventually emit like a red color wavelength, like 656 nanometers. And if it jumped all the way up to 6, okay, it had more energy. And so it then has to emit that energy in the form of light. This would be in the form of purple light as it's falling back down. So now it's time for you to do some of your own practice. No colors needed on this. So see if you can answer and match the different jumps with the different questions being asked. I'll pause, let you try to figure it out, and then I'll give you the answers. So check your answers with the answers that I have. And remember, emission is coming down and absorption is going up. Now there's some higher level math equations that we would use to figure out exactly what wavelength of light is emitted, but we've skipped that for now because it gets pretty complicated pretty quickly. But the idea is, based on how the electrons are oriented in the nucleus and in the different levels, only certain falls or only certain emissions are possible. And we can use math to figure out those wavelengths. So for all of those reasons, we can say that the emission spectrum of an atom is similar to your fingerprint, where it's very unique for every person, and the emission spectrum is very unique for every atom. And so for hydrogen, which I believe this one is, um, you can see that this pattern was created by these jumps. And so elements with more energy levels and more electrons are going to naturally have more different jumps, and so they're going to have more different more different wavelengths of light in the emission spectrum. So here's a very simple, cheap spectroscope that you could buy, and this is a simple version of what scientists use to see the emission spectrum of different elements. So you look through it and you look at that energized sample, and then you see this emission spectrum kind of right here on the screen. And these different elements have these unique patterns that are part of the whole visible spectrum. And you don't see the whole visible spectrum from each one, you just see its patterns. And like I said before, as you add more electrons, they tend to get more and more complex, but it's all a part of what we call the electron configuration, or how the electrons are arranged. And so that's going to be the topic of our next unit. But we didn't talk about the sun, and that you've seen rainbows, right? Or you've held up a prism to sunlight and it separates it into all the lights. Well, why does the sun have the full spectrum? It's not because the sun is a combination of all of the different elements, and so it's just kind of a full spectrum. There's some more complex reasons. So part of it is the huge temperature, or the super high temperature that the sun is at. Some of it is the nuclear fusion and some of the radiation coming off of that. Some of it is the Doppler effect that you might have remembered from physical science. So there's many complex reasons of why when you look at the sun with this spectroscope, you're going to see the full spectrum and not just hydrogen and helium. But remember, and I said earlier, that helium was first discovered from the sun because we were able to isolate helium's unique emission spectrum in the sun, and that's why they called it Helios, where it was first discovered. So hopefully this helped you better understand how electrons can behave like waves, and I think the explanation for the particles is a little bit simpler. So anyways, we will jump into electron configuration in our next unit, and that kind of will complete this picture. But I highly recommend going to YouTube and taking a look at more videos on the double slit experiment, Schrodinger's cat, Heisenberg's uncertainty principle, and they are all other scientists who contributed along with Einstein's photoelectric effect. These are all contributing ideas to this quantum world, and I think it will overall give you a better picture if you kind of dive into some of those YouTube videos, and there's a lot out there. So hopefully you enjoyed this.